All right, so let's talk about 4.3, the fundamental theorem of algebra and conjugate pairs. So at the end of 4.2 we talked about the rational zeros theorem, and it's a really good tool for finding the zeros of polynomials if they're rational. But if you have irrational zeros or non-real zeros, then you're a little bit stuck. So we're gonna, in this section and then the next one, we're gonna talk about a couple of tools that we have for finding some more of the zeros of polynomials if they're not rational. The fundamental theorem of algebra just tells us what kind of zeros we can expect to have. And it says this, right? So the fundamental theorem of algebra, it says every polynomial with complex coefficients has at least one complex zero. Now, if you find a complex zero of a polynomial, then you can factor it out, and the resulting polynomial, or the depressed polynomial, is going to have complex coefficients as well, which means that it also has a complex zero, right? So really, really a corollary to the fundamental theorem of algebra is that all of the zeros of a polynomial with complex coefficients are complex. So if you remember back to when we first started talking about chapter 4 stuff, we said something like, square root of or fourth root of -1 is really just a complex number. And this is how we know. It's because of the fundamental theorem of algebra. Now, I'm not going to prove this theorem to you. It's sort of beyond the scope of this course. But it's a really cool result. A couple things to note about it is that just because the zeros are complex doesn't mean that they're not real, right? So the real numbers are a subset of the complex numbers. So this theorem is not saying that the zeros are all non-real. They could be real numbers. But what it does tell us is that the buck stops with the complex numbers. There's no need to define any larger set than the complex numbers. So, for example, a polynomial like x squared plus 1 has zeros plus or minus I. X to the fourth plus 1 would have zeros. The zeros would be the fourth roots of -1. What the fundamental theorem of algebra is telling us is that this number, the fourth root of -1, is a complex number. That is, we should be able to write it in the form a plus bi, where I is the square root of -1. So how do we rewrite the fourth root of -1 in terms of the square root of -1? So that's not something that we're going to tackle in this section. We'll tackle that in the next one. But it is interesting to note that this number here is really just a complex number. There's no need to define any other set of numbers bigger than the complex numbers. Okay. Another corollary to this theorem that's important is that if we find a complex zero of a polynomial, we can factor it out, right? And then the depressed polynomial will have 1 degree less than the original polynomial. It's also going to have a complex zero. We can factor that out, and then we'll have another depressed polynomial, and we can keep peeling off the zeros until we've completely factored the polynomial down to linear terms. The factors might look a little bit strange because they might be factors where you have complex numbers as coefficients and stuff. But still, we can completely factor down any polynomial to linear terms. And but then once we've done that, there's nothing left to factor, right? So what that tells us is that if you're starting with an n-degree polynomial, you're going to have exactly n complex zeros counting multiplicity. So I'm saying counting multiplicity because you could have a zero that repeats, right? So -1 could be a zero 3 times, right? So you're not necessarily going to have n unique zeros for a polynomial, but if you count the multiplicities, then you will have exactly n complex zeros if you're starting with an n-degree polynomial. So that's kind of nice, right? So if you're starting with a degree 5 polynomial, you should expect to find 5 zeros. Let's practice. So we're going to completely factor this polynomial over the complex numbers. Over the complex numbers, we should be able to completely factor this down to just linear terms, okay? And then we'll contrast that with factoring it over the reals and then factoring it over the rationals, okay? The factorizations that we're used to seeing from our previous algebra experience have been factorizations over the rationals. But in fact, we can factor further if we're factoring over the reals, and we can factor completely if we're factoring over the complex numbers. So let me show you how this works. In order to factor this polynomial, well, let's see. Could we factor by grouping? There's an even number of terms, 3, 4, 5, 6. Yeah, I think if we group by 2's, we could probably factor by grouping. If I group the first two terms together, I can take out an x to the fourth, and we'd be left with x plus 1. If I factor the next two together, I can take out a negative 2x squared, and I'd be left with an x plus 1. And then if I factor the third group, I can take out a negative 3, and then I'd be left again with x plus 1. So that's kind of nice. Now I can factor out the x plus 1, and I'm left with x to the fourth minus 2x squared minus 3. Can I factor that any further? Let's see. This is not a quadratic, but it's quadratic in form, right? Your first variable, the exponent on your first variable is twice that of the middle one, and then the third one doesn't have a variable on it, so it's quadratic in form. I can think of this like a quadratic. So I'm going to try to factor it like this. In order to get an x to the fourth, I've got to have an x squared and an x squared. And I think I can do a negative 3 and a positive 1, and that'll give me the negative 2 in the middle. Yeah, so that does the trick, right? Now, this is not completely factored. To factor this further, what we can do is set each factor equal to 0 and solve. So for example, if x squared plus 1 is a factor, then if I were trying to find the zeros, I would set that factor equal to 0 and then solve for x, right? So I would subtract the 1 and then take the square root, and I'm going to get x is plus or minus I. Now, if you remember the factor theorem, product and factors theorem, we know that if this is a 0, then we're going to have factors x plus I and x minus I. Okay, so those are the factors that correspond to this factor, right? If we break it down into linear terms, so we would have x plus 1 times x plus I times x minus I, right? The x plus I and the x minus I combine to give us x squared plus 1. And if you don't believe me, you can do the multiplication, right? You can do x squared minus ix plus ix cancel, and then minus I squared. The negative I squared is going to become a positive 1, right? We can do the same thing with the x squared minus 3. Set that equal to 0, then solve. So we add the 3 to the other side, and then take the square root. X is plus or minus square root of 3. And so that means that the factors corresponding to x squared minus 3, the linear factors corresponding to that, are going to be x plus root 3 and x minus root 3. And there it is, right? There's the complete factorization over the complex numbers. So there's the complete factorization over the complex numbers. So now, if we wanted to factor over the reals, what that means is that we're not allowed to have complex coefficients. So in particular, these two factors are bad, right? There's nothing wrong with the square root of 3, that's a real number, but I is not real. And so if we're wanting to factor this just over the real numbers, then we need to recombine these two factors so that all of our coefficients are real. Okay? We already know that if we combine these two factors, we're going to get x squared plus 1. So the factorization over the reals would be x plus 1 times x squared plus 1 times x plus root 3 times x minus root 3. Okay? This is a complete factorization over the real numbers, because if we try to factor this quadratic term any further, we're going to end up with complex coefficients, right? which is we're not allowed to have if we're factoring over the reals. So that gives you some idea about factoring over the rationals probably, right? Because if we're going to factor over the rationals, then that means all of our coefficients need to be rational numbers. And in this factorization up here, we've got a couple of irrational numbers here. That means we need to recombine these last two factors so that we have rational numbers, so that all of our coefficients are rational numbers. So we already know that if we combine those two expressions, we're going to get the x squared minus 3 that we had up here. So the complete factorization over the rationals would be x plus 1 times x squared plus 1 times x squared minus 3. Right? And there's the complete factorization over the rationals. Again, if we try to take either of these two factors down to linear terms, then we're going to get either non-real coefficients or irrational coefficients. And we're not allowed to have either of those because we want rational coefficients only. So this is the complete factorization that you're used to from algebra, back from your algebra days. But we know that actually we can go all the way down completely to linear terms if we're allowed to factor over the complex numbers. Okay, let's do another example. So we've got f of x equals 2x cubed minus 13x squared plus 26x minus 10. An even number of terms, I wonder if we can factor by grouping. If we group the first two terms, I think the best we can do is take out an x squared. We'd be left with a 2x minus 13. Over here we could take out a 2, then we'd be left with 13x minus 5. The factors we're left over with don't match, so I don't think we can factor this by grouping. And so that means that my only recourse is to use rational zeros theorem to see if I can find any rational zeros that this polynomial might have. So let's make a list of the possible rational zeros. These are going to be plus or minus factors of 10 over factors of 2. So that would be 1, 2, 5, and 10 over 1 and 2. So we're going to have 1, 1 half, 2, 2 halves, which is the same as 1, 5, 5 halves, 10, or 10 halves, which is the same as 5, right? So there are possible rational zeros. Now we can start testing these. So I'm going to start with 1, 2, negative 13, 26, and negative 10. It's 2, 2, negative 11, negative 11, 15. Oh, 15 and 5, so that doesn't work. What about 2? Let's try 2. Should maybe write smaller because I think I'll run out of room. 2, 4, 9, 18. That's going to be a big number. 40, 8, 9, 10, 11, 12, 44. 88. Okay, so this is huge, right? 78. Notice that I get this row of all positive numbers, and I'm testing for a positive 0. So this tells me that 2 is an upper bound on my 0. So I don't have any rational zeros, or actually I don't have any zeros at all that are greater than 2. So I'm going to stop testing the positive integers. I'm going to go to the negative integers now. Right? There's no need to test 5 or 10. I already know that they can't work. 5 halves also can't work because it's bigger than 2. So I don't need to test any of these, right? None of these, on the positive end anyway, are going to work. Their negative versions could be zeros, possibly. But let's test negative 1. So I've got 2, negative 2, negative 15, positive 15. 26 plus 15, so that's what? 30, 41, negative 41, negative 51. Huh. Oh, so I get this row of alternating numbers, right? And that tells me that, so when you get a row of alternating, numbers down here, then that tells you you found a lower bound. So if you get a row of alternating numbers and you're testing a negative for a negative 0, then you've got a lower bound on your zeros. So that's interesting. So I don't need to test -2, -5, -5 halves, or -10 because I already know -1 is a lower bound. So I guess I'm going to have to test some fractions, right? I think my only hope now is that 1/2 or -1/2 are zeros. So let me test those. Unless I've done something wrong, I should check my work. 2, 11, 15. No, okay. So let's see. 2, -13, 26, and -10. 1, -12, -6, 20. Ooh, there it is. 10 and 0. So 1/2. 1/2 does the trick. Okay. So let's see now. F of x. I know that 1/2 is a 0, so I can take out x minus 1/2, and I'm left with a 2x squared minus 12x plus 20. I noticed that this factor has a 2 in common, like I can factor out a 2. What I'm actually going to do is absorb that into this first factor so that I don't have any fractions here. It's not wrong to have fractions, but I just think it looks a little nicer if I do 2x minus 1 times x squared minus 6x plus 10. Right? So I took out the 2 here and absorbed it there. So that looks a little nicer. And I wonder if I can factor that. 10 would be 5, or 10 and 1, which isn't going to give me 6, or 5 and 2, which is also not going to give me 6. So that's not going to factor any further. But I can use quadratic formula to find the remaining zeros. So let me do that over here. Some scratch work. I'm going to say x is -b plus or minus square root of b squared minus 4 times a times c. Ooh, non-real. Over 2a. So 36 minus 40 is -4. Square root of -4 is 2i, right? So I get 6 plus or minus 2i over 2. So that's 3 plus or minus I. Okay, so the complete factorization over the complex numbers would be 2x minus 1 times x minus 3 plus I times x minus 3 minus I. Okay. If you want to distribute that negative sign, you can. So we'd have 2x minus 1 times x minus 3 minus I times x minus 3 plus I, right? But there you go. That's your complete factorization over the complex numbers. Now, if we want a complete factorization over the reals, then we're not allowed to have complex coefficients. Okay? That means that we need to combine these last two factors. And if we do that, we know that we're going to get this factor, the x squared minus 6x plus 10. So the complete factorization over the reals would be 2x minus 1 times x squared minus 6x plus 10. And then finally, if we want the complete factorization over the rationals, then that means that we're only allowed to have rational coefficients. But notice that in the factorization over the reals, all of our coefficients are already rational numbers. So the factorization over the rationals is the same as the factorization over the reals in this case. Okay. So those two answers are the same. Okay. So, but anyway, you know, we can take it down to completely linear terms if we're factoring over the complex numbers, right? That's basically what the fundamental theorem of algebra is telling us. Well, it's one of the corollaries to that fundamental theorem of algebra. Another thing that you may have noticed by now is that the zeros of a polynomial tend to come in conjugate pairs. So if 2 plus root 3 is a 0 of f, then so is 2 minus root 3. Or if 3 minus 2i is a 0 of f, then so is 3 plus 2i. You can kind of see this because of the what's the word? You can kind of see this because of the quadratic formula. That's what I wanted to say. Because of the quadratic formula, right? It's negative b plus or minus the square root of some stuff divided by, something else. But that's why you get conjugate pairs, right? It's the plus or minus, the plus or minus. Anyway, so this statement is true under the right conditions. We do have to be a little bit careful about how we state the theorem. So, but here's the conjugate pairs theorem. So let's say that f of x is a polynomial and that a, b, and c are real numbers. If the coefficients of our polynomial f are all rational, so if we're starting with a polynomial that has rational coefficients, then a plus b root c is a 0 of f, if and only if a minus b root c is a 0 of f. Okay. So you get these rational conjugate pairs, but you also get non-real conjugate pairs, and this one, this second statement is true for a bigger set, right? So the first statement is only true if your coefficients are rational to begin with, but as long as your coefficients are real, then you can say statement 2. You can say a plus bi is a 0 if and only if a minus bi is a 0, right? So if our coefficients are rational, then the irrational zeros come in conjugate pairs. If our coefficients are real, then the non-real zeros come in conjugate pairs. Okay. So again, I'm not going to give you a formal proof of this, but it should make some intuitive sense for a couple reasons. For one thing, like I said before, the quadratic formula comes with conjugate pairs built in. So if you're ever using the conjugate pairs, you know that if you're ever using the quadratic formula, then you're getting conjugate pairs in some sense. For another thing, the conjugate is what clears radicals and imaginary units so that they don't end up as coefficients, right? So, for example, let's say that f of x is x minus I times x plus 2. If we were to expand this, right, we would get x squared plus 2x minus ix minus 2i. We would get these non-real coefficients. Okay. So if I is a 0 of a polynomial with real coefficients, then negative I, its conjugate, must also be a 0 so that the non-real coefficients go away, right? So now consider this other polynomial, which is the same as f, right? Except that we also have the conjugate as a 0 as well. Now if we expand this, notice that we're going to get x squared plus ix minus ix, those will cancel, minus I squared. Negative I squared is the same as positive 1, so this is just x squared plus 1 times x plus 2, and the non-real coefficients disappeared, right? If you expand this further, you get this polynomial, but it only has real coefficients. So if you're starting with a polynomial with real coefficients, then you know that the non-real zeros must come in conjugate pairs. Otherwise, you would see non-real coefficients in the original polynomial. Okay. So let me show you this theorem in action, and this is where this is a good tool for helping us find non-rational zeros. Okay, so remember in the previous section we were talking about finding the rational zeros. We had the rational zeros theorem that helped us find rational zeros, but how do we find irrational zeros or non-real zeros? Where the conjugate pairs theorem gives us some help with that, right? Like, for example, if we happen to know that root 3 is a 0 of this polynomial, then we also know that negative root 3 would have to be a 0 of this polynomial, because this polynomial has rational coefficients, and that means the irrational zeros must come in conjugate pairs, right? And the conjugate of positive root 3 is negative root 3. So what I'm going to do is I'm going to say, well, if root 3 is a 0, then x minus root 3 is a factor. And moreover, if root 3 is a 0, then negative root 3 is also a 0. That means x plus root 3 is a factor. So these two things are factors of p. that means that their product is a factor of p. So I'm going to multiply this out. I get x squared minus root 3x plus root 3x minus root 3x will cancel. And then minus root 3 times root 3 is just a 3, right? So this whole thing multiplies out to be x squared minus 3. And now I can divide p of x by this polynomial to see what I'm left with. Now, I can't use synthetic division here, right? Because synthetic division only works when you have a linear factor. And here I have a quadratic factor. So I have to use long division. But that's okay. Let's do long division. X squared plus 0x minus 3 into x to the fourth plus 2x cubed minus 2x squared minus 6x minus 3. And okay, what times x squared gives us x to the fourth? The answer is, of course, x squared. We multiply and subtract, bring down. X squared times what is x squared? And the answer is 1. We get, well, I suppose I could have brought down the negative 3 as well, right? But anyway, we get, oh, this isn't working out, though. What have I done wrong? You're all probably looking at it and see, oh, it's because of the 2x cubed, isn't it? The 2x cubed, look at me messing up. Okay, 2x cubed. Okay, 2x cubed. Let me go back. So I did x squared, I got this. Then I subtracted, and I should have had a 2x cubed there. So I shouldn't bring down the negative 3 yet. I would ask myself, x squared times what is 2x cubed? And the answer is 2x, right? So I should actually have a 2x right there. See, I knew that I was missing something. 2x times x squared is 2x cubed, then 0 x squared, and then a negative 6x. Okay. Alright, then I subtract. Those are gone. I get an x squared. Those are gone. I get a 0x. And then I bring down the negative 3. Now I ask, x squared times what is x squared? The answer is 1. Okay. Alright, this is working out now. And I get remainder 0. Just like I needed to. Okay. My apologies. But there we go. All right, there's the correct answer. So what we can say now is that p of x is equal to x squared minus 3 times x squared plus 2x plus 1. Can I factor this further? Well, I can factor it over the reals. I mean, I know that this is going to factor as x minus root 3 and x plus root 3, right? Since that's where that came from in the first place, right? This thing factors as x plus 1 times x plus 1, or in other words, just x plus 1 squared. So there is my complete factorization. So what are the zeros? Well, the zeros are root 3, negative root 3, and negative 1. The negative 1 has a multiplicity of 2. And there we see that other corollary to the fundamental theorem of algebra, right? Because if you count up the zeros, we have 1, 2, 3, 4, right? This one gets counted twice since it's multiplicity 2. So 1, 2, 3, 4, right? Our degree was 4. So 4 zeros because we started with a degree 4 polynomial. Okay, so there's an example where conjugate pairs theorem comes in handy to help us find the zeros of a polynomial. One more example of this. This one's going to be a little more complicated. It says, given that 2 minus I is a 0 of this polynomial, find the remaining zeros. Okay, well, if 2 minus I is a 0, then so is 2 plus I. Now, if 2 minus I is a 0, that means that x minus 2 minus I is a factor. If 2 plus I is a 0, then that means x minus 2 plus I is a factor. So that means that their product, x, I'm going to distribute the negative x minus 2 plus I times x minus 2 minus I. That means this factor, or this product, is a factor of p, right? So let's see what this product is. We're going to get x squared minus 2x minus ix minus 2x plus 4 minus 2i, or plus 2i, sorry, plus 2i, plus ix minus 2i minus I squared. Alright, so I've got an x squared. I've got a negative 2x, a negative 2x, and then I've got a negative ix and a positive ix. So the ix's will cancel, but I'm going to have a negative 4x, it looks like. That takes care of those. Then I've got a positive 2i and a negative 2i, those will cancel. I've got a 4 and a negative I squared. A negative I squared is the same thing as positive 1, right? 4 plus 1 is 5. So there's that factor. This is a factor of our original polynomial p. So I can perform long division on p now with this polynomial to see what I have left over. So x squared minus 4x plus 5 into x to the 5th minus, I should say 0x to the 4th minus 10x cubed plus 10x squared plus 29x minus 30. Let's see what we get. What times x squared is x to the 5th? The answer is x cubed. And then we multiply. And subtract. 4x to the 4th minus 15x cubed. And bring down a 10x squared. Okay, what times x squared is 4x to the 4th? I think it would have to be 4x squared. Minus 16x cubed plus 20x squared. We're subtracting now. We're going to get just an x cubed minus 10x squared plus 29x. Okay, this is going to have to be times x, right? X cubed minus 4x squared plus 5x. Subtract. We're going to have a negative 10 plus 4, negative 6, right? Negative 6x squared plus 24x minus 30. So then I think this is going to have to be a minus 6. Okay, so negative 6x squared plus 24x minus, oh, look at that, beautiful. Okay, remainder 0. So what does that tell us? Well, that tells us that our original polynomial p of x is x squared minus 4x plus 5 times x cubed plus 4x squared plus x minus 6. Very good. Now, we're supposed to find the remaining zeros. We know that the zeros that come from this factor are 2 plus I and 2 minus I, since those are what were given to us at the beginning of the problem. But we want to find the other 3 zeros that come from this factor. Can we factor this further? Can we factor it by grouping? I don't think so. We could take out an x squared, we'd be left with x plus 4. Here we can take out a 1, we'd be left with x minus 6, but the factors don't match, so we can't factor by grouping. So, rational zeros theorem. Here's my list of possible rational zeros. They're going to be plus or minus factors of 6 divided by factors of 1. Oh, that's nice. So it's going to be plus or minus 1, 2, 3, or 6. Those are the only possibilities. So let's start to test. I'm going to test 1 first. 1, 4, 1, negative 6. 1, 1, 5, 5, 6, 6, 0. Look at that. Okay. I'm running out of space, so I'm going to come back over here to the side of my paper. But what I just discovered now is that P of x is equal to x squared minus 4x plus 5 times x minus 1, right? Because 1 was a 0. We just found that 1 was a 0. So times x minus 1 times x squared plus 5x plus 6, right? Now, can I factor that thing any further? I think so. This is x plus 2 times x plus 3, right? So we've got x squared minus 4x plus 5 times x minus 1 times x plus 3 times x plus 2. There we go. So they're all the zeros, right? So the zeros. Well, first of all, from this factor I have 2 plus I and 2 minus I. And then from the remaining factors I get 1, negative 3, and negative 2. 5 zeros, right? Started with a degree 5 polynomial. So there you go. That's how you find, that's how you would use the conjugate pairs theorem, right, to find the zeros of a polynomial. So it's a nice little tool. That's all I have for this section. In the next one, we're going to talk about another tool that we can use called de Moivre's theorem.